So to get these points to animate, what I want to do is bring in another point deformer. So let's throw down a point deform, and I'm just going to bring the thing that we want to deform, which first off is this, which is our wires here. We don't want to deform all of them. I just want to deform the starts. Remember, the starts are these points right here that are attached to the body. And the way I want to deform them is using the actual motion of our RBD objects here. So we've cached out, we've got our RBD simmed character and then our time shift here, which we're locking at frame 0. So remember how down here we want the rest point lattice and the deformed point lattice. We can do something similar here. I'm just going to wire this rest point lattice up to the time shift here. And I'm just going to create a little elbow out by holding down the Alt key so that that's sort of out of the way. And the next thing is we want a deforming point lattice. So I'm going to pull off the RBD simmed character. I'm going to pull off a wire, create another elbow, and go all the way down here and wire that into the deformed point lattice. So now if I highlight this and click play, you can see just those first points are moving around. It looks kind of weird for this, but it's going to work for our simulation because we've pinned these points to match animation. So let's wire this now into our sim instead. And now I'm looking at this. It looks like this point deform. I'm going to just do a little wire organization here and actually break these elbows off to the right hand side so that they're out of the way here. And then maybe I'll set a couple more notches down here just to get those nice node paths out of the way. And let's just jump back to our Vellum sim over here. And you can see I'm just going to go back to frame 1 and click play. Now you can see all these wires are nice and attached to our character. And as our characters, you can sort of see a vague outline of our character doing handstands and all the such, which is cool. And now you can see all these pieces coming apart because our character has now broken apart into a bunch of pieces, which is cool. What I also want to do is let's bring in a collider object so that these wires are actually colliding with our sim geometry as well. So I'm going to throw down a static object, and for the static object I'm going to select another SOP path. I can actually just bring in, it looks like our RBD simmed character right here. This is the kind of geometry we need. The RBD simmed character is actually actual geometry that's deforming. So if I just grab the RBD static object and drag our RBD simmed character node into the SOP path and tick use deforming geometry and go back to frame 0, and then I'm just going to merge it in to the merge it in with the ground plane. So I'm going to select the ground plane in the static object and wire those guys in, and then set this wire in the bottom of those, in the bottom of the merge. And now you can see that geometry in our scene. And what I'll do is just go to the static object. I'm not sure what the default solver is, but I want to use surface collisions, and go to the surface and say show collisions. You can see that's our collision geometry that it's going to be using with our wires. So now it's kind of hard to tell because there is a lot going on, but these wires are now attempting to collide with the geometry as they're being manipulated and pulled around by it as well. So we got those constraints and the collision geometry now affecting the simulation. So we'll just let that play for a little bit and see what we see. You can see that there's a lot of jagged lines. The wires are pretty loose at this point. There's some strange sort of collision things happening with the wires. So these are all sorts of things you look out for when you're running a sim like this to see, what kind of things you're going to have to clean up. And here comes our geometry just kind of breaking apart like so. It's pretty cool. So now a lot of like these glitches and stuff can be fixed with doing things like increasing substeps, increasing constraint iterations, doing some smoothing in the end. Maybe even in the case of my example, I think I even found wires after I did all that I wasn't happy with, and I just grabbed, you can just art direct after the whole fact and just say, yep, don't like this wire or whatever it's doing, and just delete it from the sim if you don't like it. But at this point, let's just start to make this thing a little bit more interesting. So I'm noticing, first off, these wires are they're all staying connected, and they're all pretty loose. And I also want to create some additional wires that are sort of connecting in between them, so it kind of gets more of this spider web like effect. So we're going to be breaking our wires into pieces that will then reconstrain together and then apply like a stress to, and then they will break. So we can do that. I think that what we'll start off with is we will start by breaking all of these wires up so that they can be broken during the simulation. So at this point, before we move any further, I just want to double check and make sure that the crag geometry is able to keep up with what we've done so far. So I'm just going to go up here to the top of my network, and I'm going to just wire in test geometry crag into the input animation and see how it flows through our network. So if I go down to this first point deform and highlight that and just frame up our crag, and just I'm going to go navigate over here and just kind of play it back a little bit. You can see that we've got a little bit of some, it looks like some breaking that's going on with our input. It looks like, I mean, we're able to deform all these pieces, but this hammer is not following accordingly. So what we need to do is we actually need to convert this geo. So let's just run on a convert. And if I convert that and then send it back through, and let's go back to frame 1 and play this back. You can see that the geometry is all deforming accordingly. But what happened was this little this bar of the hammer is actually not sticking to the is actually sticking to the forearm and not the rest of the hammer. And this is where that little section came in that I had mentioned at the beginning of the lesson, the message from the future, if you will, where we did a little bit of additional setup to fix that. So I'm just going to copy that out of the start project and paste it into this one. So I'm going to go over here. You can see we've got the start project here. I'm going to just grab all these nodes, control copy, and minimize that. I'm going to go up here and control paste that. So now you can see that it automatically detected that test geometry crag is what it wanted to wire in. I'm going to delete this old convert, and I'll just wire the crag animation into the input animation. So now when we go back down to this point deform, because we've added a bunch of geometry to this handle, it should now be able to handle this point deformation. So let's go back to frame 1 and click play, and you can see that all the spheres along our handle are following along nicely. Great. So let's just test and see how it goes through this DOP network. So I'm going to highlight the DOP network, and we will play it back, and it's going to kind of go through a little bit, and then it should eventually reach a point where it's all going to fall apart at frame 128 or whatever we had set it up for our dancer. At this point, you could probably choose whatever frame you want to have the crag become destroyed, if that is what you're after. But since we chose to use frame 127 or 128 before, I'm going to just let this kind of go out, play out until then, see what we get. And crag falls apart. Looking good. So now that I've got all this simulation stored in memory, I'm going to just I'm going to bypass this cache, and then let's unpack it and then convert it. If I go to this, you can see that we've got our, I'm just going to turn off this template flag. You can see we've got our little geode looking things. And we can go down here to this point deform and see if it is pulling our vellum object along nicely. And it looks like it is. And if we just go over here to our sim and test it, looks like all those chords are adhering to our crag geometry as well. I'll try to check up on this from time to time. I believe that getting to this point, though, everything should be fine from here on out. All right, so let's go back and switch it back to our mocap dancer so we can proceed with the lesson. So back to our mocap dancer, you can see how nicely that changes up all the geometry, and we're already ready to sim again. Just crazy. It's actually, because I have this RBD cache turned off, it's actually simming both those networks at the same time. It's first simming our DOPNet right here, and then it's doing our vellum sim. It's doing it all on the fly, which is really cool. But since we don't need to be recalculating this sim anymore, I'm just going to turn the RBD cache back on. And we're going to focus on now splitting apart these wires so that they can snap apart when the dancer puts a certain amount of stress on these points. So let's go down to, let's see, let's go down here so we can split apart these pieces. The way I'm going to split them apart is I'm going to do it inside of this for each that we used before. So let's just make this a little bit bigger. I'm going to slide this over here maybe a little bit. Inside our for each here, we can create another group using another group by range and just select one point in the middle of each one of these primitives. So let's get in here, and I'm going to turn on a single pass again like we do to see our one of our lines here. I'm going to turn on the points display, maybe the point number, and also actually not the points display, but the point. No, I'm going to throw on the primitive number. So you can see it's kind of hard to see. Let me see if I can turn up my guide font to large. And you can see there's a 0 on the middle of this, denoting that there's only one primitive. If we look down here in our primitive spreadsheet, there is just one primitive there. So we can use a group. We can find a point and actually split this polygon based off of some point that we put into a group. So I'm going to use a group by range. Again, hit tab, start typing group range, and throw this guy down here. And the settings I want to use here are a little bit trickier. I don't want to split this. What I could do is, let's first set this up. We'll call this a split group. Splits. And it's going to be a point group type. And we're going to want to, we can use this range filter to select one of two. We could, select every other point if we wanted to. You can see that the blue ones are actually the non-selected points. The orange ones are the selected points. So we can select by different ranges this way. But I want to just select one point randomly in the middle of all these points. So if I say I want to select one out of however many points we have here. How many points do we have? Looks like 74 points. So I want to select one of 74 points. I could just type in 74 here, but that wouldn't work because for all these other primitives that we have here. 74 is only the number of points in this primitive that we have. So that's not going to work. What we're going to have to do, we can set this offset here. You can see if I offset this group, now we can set this to somewhere in the middle. Like we could set it to 35 or something like that. And that would be a point in the middle of our prim that we could split by. Let's turn off these point numbers real quick. So we could do something like this, but if we switch to another pass that is shorter and is therefore resampled less, there's no group created because there is not 74 points in this group. We'd have to bring it down to some other value like this. So we can use actually like a little expression here to just look at the number of points that are in the input and use that number of points to determine our range. So we're always going to want to select only one point, but we're going to want to select one point out of the number of points incoming. And the way we can do that is just typing in n points of the 0th input, which is just whatever's flowing into this node, basically. And it's going to select one point out of all those points. And so now when we go through, if I click on the group range, but then let's see if I can, yeah, if I click on the group range and then go down to this single pass, it doesn't really show. But if I just kind of switch back to our first our 0th pass here in the single pass field, and then click, you can see that it is grabbing some point in the middle, and it's grabbing it's offsetting that by 35 from no matter what the size of the point range is. Well, I want to select a random point now. I don't want to select one that's too close to either end, but I maybe could give it a little range in the interior in which we could select a point. So we can use another expression here. And I'm going to just click on this offset so that it makes this text larger. And I'm going to just type in a simple random expression. So what I want to do is create we've got, if I middle mouse click here, we've got an ID that's incoming. So we can use the ID as our seed. So in here, I'm going to want to create a little expression. We're going to want to use a random expression and then fit that random expression between some range that's close to somewhere in the middle, but not anything but basically the endmost points. What we need is a random seed for each loop of this iteration. If I go up here, we've got ID attributes, but those are actually point attributes, which isn't going to work. What I could do is create a meta import node and then use the iteration of the loop to determine to determine our random seed. So I'm going to click this first node right here and say create meta import node, and that creates our meta import node here. I'm going to just rename this meta, and down here in our splits, what I'm going to do is create a spare parameter. So we're just going to go here and say add a spare input, and I'm going to drag the meta in there. So now what we can do is use a detail attribute to look up our random seed. So if I type in rand of detail, and I want the detail from the spare input, the way to get that is to type in -1. This spare input is really the -1th input, and the attribute we want is iteration and 0. And this is just another one of those little functions and setups that you kind of get used to after a while. We've done this a couple times already now, but really it's just about, checking a detail attribute on this meta import node. This meta import node knows which iteration we're on in our loop, so we can look that up and use it as a random seed in the generation of a random number. So if I close this now, we get a random number between 0 and 1. Which isn't very helpful because it's going to keep most of our stuff towards the end here. But we have the fit range node. In fact, the fit 0, 1 node will take a value that is already mapped between 0 and 1, such as a random number, and we can fit it to a new range. And let's say what we want to do is fit it between a minimum and maximum of 25 and 75% of the number of points coming in. So like we're setting sort of a random boundary on the inside here. So what we do is we could say maybe 0.25 times the same thing right here. I'm just going to copy endpoints and just paste it in. So we're going to fit this range from 0.25 times endpoints of the incoming and 0.75 of endpoints on the incoming. Now, we get a random number that's positioned here, which is sort of, it's not directly in the middle. It's not too close to the ends. Let's just increment up to the next pass and see where it grabs a point for us. You can see it kind of grabs it from a similar area here. Hopefully this is random. And let's go here and see where it grabs that point. Seems like it's closer to the middle. That's cool. I'm going to make this a little bit more extreme maybe on this expression. Instead of it going from 25% to 75%, we'll go from 10% up to 90%. So our range is even wider. So now we've got that. Let's go back to frame Let's go back to frame the single pass 1. Cool. I'm going to just turn off single pass, and then just try to instead of, you know, before when we were checking where our starts were, we were blasting away all these points. So we can just throw down this, we can use this blast we already had throw down here, or you can throw down another one, and we'll just choose our splits. And it's going to say, we're going to say, oops, I don't want starts in there, just only splits, and say delete non-selected. And then let's template our previous geo, and you can see that these split points are at all different points in our strings. We've got one that's up here towards the end. This one's sort of a little bit more towards the middle. This one's very close to the end, and so is this one right here, and that one. So that's looking like a cool, looking like a nice random distribution that we can use for our split points. So I'm going to go back here. I'm going to turn off the point display now, and you can see that we still have these primitives that are all still one primitive per piece. So the next thing we're going to want to do is use a poly split and use the split group to break these polys apart. So over here, I'm going to just zoom back out a little bit and bring our point deform down, and maybe I'll bring these elbows down as well. And we can just come in here and throw down a poly cut. And if I highlight the poly cut, nothing is being cut. You see right here, we've got this field where we can define our cut points. So what we want to do is put in the splits that we defined before. You can see that it is breaking apart these primitives. Now you can see there's this little gap in the middle here, and the primitive numbers are now assigned to 2 per thing, 2 per line. And instead of removing these split points, we can just change our strategy here to cut. So now those are connected back together, which is what we want. We don't want them to actually be deleted. So it still looks like a continuous line, but now we've split the primitives apart. So I'm going to just turn off the point display and the primitive numbers, and let's just go back into our Vellum sim and see what happens. So now I'm just going to click play here, and you can see that all of those points and all those wires kind of break off and dangle on their own, which is cool. But we actually want them to stay connected until we apply a certain amount of stress and then break things apart. So how are we going to do that? Well, we got to add some new constraints to stitch these points together. So the way we do that is back over here in our Vellum setup here. I'm going to just throw down another Vellum constraints node. Vellum constraints, and if I just hold it under here, and it seems to like it's smart enough, it can pick up these 2 streams at once and wire them through, which is cool. So for the Vellum constraints, we actually want to use a let's actually use not a distance constraint, but up here at the top where it says constraint type, we're going to choose stitch. What is it? Stitch points right here. And the group type is going to be points, and the target group type is going to be points. So we set those 2 to points. And let's see what we get now in our sim. So if I click play, now it's as if our geometry has been connected back together, which is good. But now one thing that I really want to do before we move too far ahead, along with trying to get these constraints to break, is I actually want to set up some initial tension on all these wires. You can see how when we play this back, they all just kind of droop down. I actually want them to kind of like almost appear like they're tugging on our character, so that there is some tension there for which to apply some sort of breaking in a way that looks good. So to do that, what I want to do is actually mess around with some of these initial hair constraints. So up here on our hair constraints, you can see that we have this thing called the rest length scale. And basically what rest length is it's going to compute the length of all of these primitives and determine what its initial length was and store that as its rest length. If we do a scaling on that, it's going to want to try to get these primitives to adhere to whatever the original length was times this scale. So if we create this scale, if we make this scale a little bit smaller, it's going to try to make these strings contract to achieve that smaller rest length. So maybe if we bring this down to a value of like 0.6, and let's check out what our sim is doing now. So before we had this nice droopy behavior with all these wires, let's see what happens when we set the rest length. I'm just going to control click the brain so it resets the sim. Select a node over here and click play. You can see here that they're not drooping as far, but they're really not staying that tight as well. So we could do something like, maybe decrease the rest length scale even further. I'm going to try something insane like 0.1 and then click play. And you can see that all sorts of weird kind of stuff is happening. The rest length is too short and it's having a hard time kind of keeping track of what's going on. So we need to kind of fix this. And this is where the delicate dance of trying to balance all sorts of different factors in your sim come into play. Back where I had this rest length set to 0.6, I want to keep it at 0.6. And let's just give it a little play and see what we got. You can see that the wires are falling, but they're not like super tense. This is where it gets interesting. In the Vellum solver, this is where you got to kind of mess around with your constraint iterations. If you actually increase the constraint iterations, it's going to run through all these constraints and refine them in a more accurate way. And it can actually drastically change the look of your sim and in fact like almost change the physical properties of the sim because it's becoming more and more and more accurate and it's giving itself more and more opportunity to correct these constraints. So it's not, it's sort of something you get used to. You're going to run into situations where you're doing a ton of trial and error. I think it maybe took me like 10 or 15 tries before I found the right settings that worked for my example here. So, if you're going through these things, don't get frustrated. Just take your time and kind of go through and see if you can arrive at the correct settings. It's something to get used to for sure. But what I found worked for my situation was I'm actually going to crank these constraint iterations up to 500. And you can see immediately what kind of what kind of difference this makes in our sim. So if I click play, now you can see that these wires are all like super tense and feeling very much connected to the body as it moves through the scene, which is good. It's going to become even more obvious when we add our additional webbing in here. So let's do that right now and see what the additional webbing is going to get us for our sim. So let's go over here, and to create the webbing, I actually want to make our webbing based off of these splits that we created over here. So to do that, we're going to make another branch over here and just create some additional connected points, or connected lines that we can use in our sim. So let's throw down a blast. And we have a blast here with our splits on it. I'm just going to use this. So we've got a bunch of points here. If you don't have this node or you've deleted it, you can basically just choose splits from your group and delete non-selected. And here, I'm gonna throw it on another node called connect adjacent pieces. And connect adjacent pieces is kind of going to do the plexus thing. If we highlight it and choose connect adjacent points, we can crank up our search radius, and it starts to kind of do a little bit of a plexus like thing. I think that, let's see, I can bring the search radius up pretty high like that. Maybe I'll bring the maximum number of connections down to 6. That looks good. So, I mean, I don't want to create like too many points, but something like this just to add a little bit of interest to our scene. Looks like I'm going to just be adding, it looks like 133 primitives. Sounds good to me. So, that's all good, but the only other thing is that remember how we resampled our polys over here, we've got a pretty dense point count here. We're just going to want to resample these as well so that they kind of work. So that they work along with the sim in a similar way. So let's go down to resample. Let's just wire this in here, and I'm going to go and actually, in case we decide to change our resampling settings later on, I want to actually use whatever the resample value is for here. So right here we set our resample to be a length of 0.05. I'm going to right click, copy this parameter, and go down to this resample right here and select that, right click, paste relative references, and then sometimes it's got these extra zeros on the end. You just got to delete those and hit enter. And now the distance between points for our connected JSON pieces should be similar to that of our polycuts. And now we can just merge those together and feed that result into our sim. So I'm going to wire polycut and resample into here, and then we're going to merge that all down into the point deform. So now when we go back, I'm going to turn off the point display, and let's hop into our Vellum sim once again. You can see our dancer is sort of surrounded by this interesting looking web of polygons, and now because we've decreased that rest length scale and increased our constraint iterations, I'm going to click play again, and you can see that they all sort of contract briefly and get sort of like sucked in around our character, which is kind of cool. So that's all working and looking pretty cool. Still a little jagged around the edges, but I'm not going to worry about it for right now, just so we can get, because really what we want to do is we want to get the braking system worked out. So why don't we go back into our stitch constraints and turn on braking. So braking is located here on our Vellum constraint stitch. And let's just click that and turn it on. And go back to frame 0 and select a node over here in our sim and click play and see what happens. You can see that all those strings kind of break apart instantaneously. And that's because this braking threshold, basically it's evaluating how much stretch stress is being put on our primitives or on those stitching areas right there, and then breaking them according to that. So let's just crank this up to something like 1 and see if we get a different result. So it's going to go back to frame 0, click play. So some breaking has occurred, but a lot more of them have adhered and stayed together, and we even have some pieces still connected to the wall. But all in all, it is way too much breaking for this early on in our setup. I sort of want this breaking to continually progress as we go through our simulation. So I'm going to go back to frame 0, and I'm going to set this to a value that I had found for my example to work, and I used a value of 1.7. So let's go back to our sim, select a node over here, and click play. So it looks like we've got some pieces kind of breaking off. A lot of them are still staying connected, but as the dancer is moving around, more and more pieces are going to sort of become detached from the sim, which is cool. We've got this foot moving here. That's good. I'm just going to let it play through a little bit further to see, how these constraints handle as we get through our backflipping sequence and everything like that. So I'm just going to play this back sort of in real time, just whatever's in the cache. And I'm going to go to my camera 1 view. And I'm liking how things are sort of sticking to our character and following along. But then right here, there's a little bit too much attachment after the flip. So I think what I'll do is during this backflip right here, I'm going to just manually go and break the remaining stitch constraints that are on our setup, so that we still don't have these pieces that are connected to pieces on the ground once everything comes crashing and breaking apart. So let's do that. To update our constraints manually, I'll pick a frame, like say I want all the chords to break at about frame maybe 124, something like that. So to manually set a constraint, in the sim, we can actually use a vellum constraint property node. Vellum constraint property, and I can just wire this in here. And in here, you can see we get all these different options like rest length, damping ratio, rest length scale. What we're worried about here is the break threshold. So now, if I go and take my break threshold and set it to 0 again, and go back to frame 1 and click play, we're kind of back to where we started from. All these constraints are breaking immediately, and that's great, but we want it to actually be delayed and happen later on frame 120. So the way I'm going to handle it is I'm actually going to do something similar to what we did with our RBD object, which is if you go up here to the top, you see we've got this activation parameter, and we can just keep this vellum constraint property node deactivated until frame 124, and then it's going to overwrite. So just to test this, I'm going to do some lower frame, like, maybe frame 10, and just see what happens when I set this activation value to true after frame 10. So again, like I like to do, I'm going to put in a $F is greater than 10, and that means that anytime this value goes to over frame 10, so on frame 11, this expression is going to evaluate to true. So let's go back to frame 0 and click play. So everything should continue to stick together, and then boom, on frame 10 everything breaks apart. See, we're still getting our initial breaking thresholds, like this wire over here is breaking off, and it's still doing everything we want it to do, except we're actually manually able to override it and tell all of them to break at a certain frame that we want it to all break on, which is great. Cool. So I want this, I think we decided something like frame 124 would be good. So I'm just going to go back and modify this expression to break on frame 124. So or maybe 123. Oops. So any time this frame number is greater than 123, it's going to evaluate this expression to true, set the breaking threshold to 0, and all of our constraints are going to break. All of our stitch constraints are going to break. So at this point, what I would like to kind of try to address is, if I look at my simulation, I'm just going to zoom in here and scrub through a little bit. It's kind of hard to see because there's kind of a lot going on. But if we look right around here, you can see that there is some cables that become tangled around one another, and after a while they eventually just leave and intersect one another and become untangled. Now this, I mean, is it really going to be noticeable in this gigantic sim with all this stuff going on? Maybe not, but in order to sort of remedy that, and this may or may not work, I want to increase the collision passes as well. This is just another setting on the vellum solver. So I'm going to increase the collision passes to 100 and click play. And this, you'll see now the simulation is going to be getting much, much slower to calculate. But as we get over here, you can see it is doing a little bit better at keeping those wires kind of draped around one another. And now this all varies depending on how many wires you have in your scene and everything like that. You might need to crank this up higher. Adding sub steps might help. And it also, to a certain extent, I mean, I don't really feel it necessary to get super accurate with this one, because likely if something's bothering me, I'll just delete it later on or whatever, just to get it, just to kind of get it looking nicer in the end. I feel like with the number of wires we have in this simulation, it looks pretty chaotic and crazy anyways, so I think we might be able to just get away with cheating it a little bit, if there is any weird artifacts like that in the end. So let's just go and cache this out right now and see what we're left with. I'm going to go out of my DOPSIM and into this hair vellum. I'm just going to rename this vellum export and just dive inside. You can see we get the vellum IO node that it makes for us. I'm just going to save this out to a different file. I'm going to put it in my cache folder like I like to do. So cache /$OS to name after the operator, and $hip name to sort of serve as a version where we keep our sequence of cache files. And from 1 to 160 is good. I'm going to just rename this to vellum cache just because, I don't know, I'm not... Whatever, personal preference. You can name it whatever you'd like. I just want my folder to be called vellum cache. I like to name my cache folders with the word cache in them. So I'm going to hit save to disk, and I'll be back when this is done caching. All right, so the sim is done caching, and I'm just going to go to this cache node, and let's play it back and see what we got. And let's maybe play it back so we can see our character in there. I'm just going to hop up to the top level, and I'm just going to make sure my vellum export and my animation are set to display. And I'm going to go and grab and set the display flag to the RBD simmed character inside of my animation node. So back out here on the object level, I'm just going to select my select key so that pivot goes away. And let's just play this back. So our constraints are breaking. All the wires are nicely draping on one another, which I like. But then there's a couple issues here towards the end and in the middle that are kind of bothering me. So let's just kind of get a top view here. One of the things is, once the pieces come crashing down, it looks like there's still some constraints that are pinned to the surface of this object. And I kind of want those pins to break as well once we get down here. You can see there's just some straight lines that are sort of affecting the way things are looking. So maybe what we could do is we could release those pins from this character when it crashes into the ground, just so that we don't end up with things like these straight lines being dragged apart by the spheres themselves. So that's one thing we can fix. Another thing we can fix is if you go down here, I've found that when I was running this, having points that are projected directly below the object can kind of create some problematic stuff, like these constraints are just sort of sticking out and not really doing anything. And I find constraints to be kind of hard to troubleshoot. So rather than fixing this, using by trying to debug them, I think what I want to do is just sort of limit where these constraints are allowed to actually spawn. And the way I'm going to do that is by actually deleting points that are facing in the downward direction. So let's do that first. Let's go up here into our animation, and I'm going to go and right here where we've got our scatter, I'm going to actually throw down a delete, and I'm going to delete points based off of their normal. So if I throw this delete down right after the scatter, I can set it to point mode, and we're going to disable the number but turn on the normal. I'm going to enable that and set it to a value of direction to 0, -1, 0. And then I can just decrease this spread angle, and you can see that we're slowly getting rid of points that are being projected downward, including like this point right here, which is really kind of an issue. So I might try and bring this spread angle up to a point where those points kind of disappear, so everything is sort of surrounding our character. What I might do at this point is also, I think maybe we could go with some more points, some more scatter points. So I'm just going to increase the scatter count You can see after this delete, we're down to 33 points. We did have 50 points, and we managed to delete 33 because of this normal facing direction. If I go back up to the scatter, I'm just going to crank this up to 100. Just to get back closer to where we were with those 50 points. So yeah, now we've got 70. It looks like 69 wires that are connected to our character. So that's cool. But none of them are really pointing downward per se. So if we go back down through all of our stuff, we get more of these web-like connections, which is which hopefully will look cool. And so now we can sort of so that's sort of going to take care of those issues that we're having on the floor here. And then the next thing I want to do is actually do another setup where we tell these constraints to, we tell the pin constraints that are connected to the body to break at a certain point. And now what I'm going to have to do in order to get that to work is I'm going to have to kind of split this up. So we've got our start points, which are near our character, and our end points, which are constrained to the wall. We need to actually have the start points be handled differently from these endpoints that are connected to the wall. So I'm actually going to take the starts out of our pin group here. So only ends are going to be pinned to the wall. And because the wall is not animating, we no longer need this match animation turned on. So I'm going to just take this section and move it over here so that I can refer to my input geometry on the right. And in here, I'm going to just select my vellum sim so that I can refer to my vellum sim on the left. To make things a little bit faster for the time being, I'm going to turn the collision passes down to 10 again. We'll just crank them up again next time we do a cache. And I'm going to just play this a little bit and see what we end up with. This should all the pieces connected to the body should just fly away. And that is looking like it is working correctly, except we may have some collision going on, but in large part, the constraints have been fixed for that. At least they've been detached. Now we have to reattach them using a separate constraint node. So I'm going to throw down another vellum constraint. Vellum constraints node. I'm just going to wire this right in between the hair and the stitch constraints. So I'm just going to drag that in there. And we're going to select our type is going to be pin to target, like this. And it's going to be a point group, and the group is going to be our start points. So you can see here that it's added, it's signifying that we are just pinning these start points right here with these little blue kind of spheres that appear in that area. So now if I go back and tick match animation here, and we head back over to our vellum sim, we should be sort of back to where we started from. So if I click play, all of our pin constraints are connected to our object. That's looking good. And we've got braking occurring still, which is good. And so we can kind of, we can proceed from here, but what we want to do is we want to actually get this to break as well. And the way we can do that is we've got this, our pin to animation pin type is by default set to permanent. We can actually use this stopped mode, and stopped is going to behave in a similar way to the way we activate and deactivate things. So by default, this pin type is stopped. So if we click play, stopped basically means that it is pinned to the animation. But we can actually get this pin to release by changing its stopped value to 0, and that will actually turn it back into a dynamic constraint and essentially break it. So the way I want to do that is I'm going to set the stopped attribute using a point vob, or a pop vob. Not sure why it's giving me an issue there, but it looks like it's gonna let the show go on, which is good. So in here, I'm gonna wire this into our merge, and I'm gonna dive inside. And the attribute we want to change is stopped. So I'm gonna put down a bind export, and I'm going to set this to stopped. And I'm going to just use a constant value. And set this stopped attribute that's being bound out is actually going to be an integer attribute, so I'm going to set that. And this constant value is also going to be an integer. We want to use the integer value to set an integer attribute, and I'm going to wire that in right here. And if we go back up here and click play, you can see all those points kind of fly away from the animation. But you can see that they're doing something kind of weird. They're actually sort of kind of following the simulation even though they aren't connected. To make this maybe a little bit more obvious, I'm going to just hop back over here and maybe decrease temporarily our scatter back down to a value of 50 just so there aren't so many points in our simulation. And maybe what I'll also do is let's just bypass this merge here so we don't get any of these extra webs, and we can kind of analyze what's going on here. So we've set the stopped attribute to 0. But all these points are still almost behaving like they're connected. You can see the movement of the character still appears to be having an influence on all of these points, which is not ideal. We just want the points to, we want these constraints to release and then stop being, so it's like, what's going on here? Well, there's other attributes that we want to change. So because on our constraint over here where it's pin type is set to stop, but it's still set to match animation. If I go and middle mouse click on here, you can see we've got these attributes. One of them is a point attribute called glue to animation, and then we've got our stopped here. So we've got other attributes, but when I see this glue to animation, that's sort of another clue. So if we go over in our vellum constraints here and just select our point attributes, and I'm going to go to hide all attributes and show glue to animation and show stopped. I'm going to sort by glue to animation. You can see that all the stopped points, which is stopped is set to a value of 3. I'm not quite sure why, but basically anything that has a value under stopped is also set to glue to animation. Then everything else is to 0. So what I thought at this point is, oh, we could also turn glue to animation off as well as stopped. So let's just try and add that into our pop-up. So stopped, I'm going to actually just alt drag this down to make a new bind export, and I'm going to just change this value to that glue to animation value. So if I go under my vellum object here, just want to make sure that that's what the attribute's called over here. Go into geometry, under vellum object geometry, we can see our attributes here. I'm going to hide all the attributes, but I want to see the stopped attribute right here and the glue to animation attribute like that. And so if I just bypass this stopped attribute and sort by the stopped attribute, I'm going to just bypass this as well. I'll go back to frame 0 and sort by stopped. Click play. Maybe sort by glue to animation. Sometimes you got to toggle back and forth between these two before it actually lets you sort. But so now we've got our stopped attribute here, and we can change it. We're going to change this in a similar way to how we did the vellum constraint property here. So let's just temporarily try to deactivate these constraints at frame 10. So I'm going to say $F is greater than 9. So it'll play for 9 frames, and then it should activate this pop-up. So if I turn this on and I turn on stopped, and this one I've never named to glue to animation. I got to name this after that attribute. So glue to animation with no spaces, like so. So now we can watch our attribute spreadsheet, and all these glues should be changed by this pop-up at frame 10. So let's click play. They're connected to our object, and then at frame 10, they all go flying away. And do they continue to kind of dance around with the object? It doesn't look like it. It looks like, I mean, they do have a little bit of their own sway, but they're no longer being influenced by the object anymore. So that's really good. We're able to release all of our original glue constraints or pin constraints, no problem, at whatever frame we want to. So I think that for our purposes, we'll want to kind of release them maybe in the middle of the crash. So as these rigid bodies come down like this, maybe we release the remaining pin constraints at frame 134. So instead of $F is greater than 9 on our pop-up, we'll just set $F is greater than 133, something like that. So now all these pin constraints should remain attached to the body, but then they will release in the middle of the when the body comes crashing down. Cool. So now to get this back to a point where we've got all of our web and everything and our increased number of polylines, let's just turn our merge back on so we get all these connections back, and we'll just go up to our scatter as well and crank this back up to 100. That almost seems like a little much. It might obscure my character a little bit. Maybe let's try bringing these maybe 64, maybe a little bit more. It's interesting because it reseeds every frame. You can kind of do a little bit of mini art directing here. Maybe I'll put my camera in and also template my RBD simmed character just so I kind of have an idea of what I'm getting out of these different scatter patterns. I'm just going to use the ladder so I can step slower through these. I don't know, this is looking pretty cool. I kind of like how evenly distributed it is in the frame, so I'm using force total count of 65. 65 points seems cool. So now we just got to remember, when you're changing settings, you got to remember to change them back. So the collision passes has to go back up to 100 as well. And then we can run our sim one more time. But I almost forgot. One final thing. If we look at our, if we go and look at our previous cache, I'm going to just kind of frame this up. Let's go over here and select our Vellum export here. And I also want to show our room. I'm going to hide this animation and just take a look at our room. And let's go in by our camera and select the camera and view it. Might notice none of our wires are actually colliding with the room itself. So if you see this wire in the back right here is actually penetrating through the wall. There's a few wires that are penetrating through the wall, and they're coming out the other side. So when our wires release, we're gonna want those wires to actually collide with the wall so that it all feels like it's, you know, in that room. And so to get that to be resolved, we're going to add another static collider into our scene over here. So I'm going to throw down a static object. I'm going to just name this static object, even though it's, whoops, hit escape a couple times. Even though this static object is kind of is deforming, I'm going to call this the character collider, just so we know what that's supposed to be. I'll create a new static object here and we'll wire it in. It doesn't matter what order these are plugged in over here in this merge, but this one will be called our room. And for geo, I'm going to grab our cusped room. I'm not sure if it matters, but cusped room seemed to work for me. Again, that was the one that was separate pieces. And let's see, I'll maybe set this also to be a surface collider, just in case it matters. So I'm showing my collision rays. All right, that's looking cool. And I guess to just test this without collision pass, I'm just going to lower the collision passes real quick just to make sure that this works. So I'm going to hop back into my camera and let's click play. Until some of these wires start snapping apart and colliding with the wall, so we can see if they're indeed colliding with the wall. Is any of that happening yet? I certainly don't see anything coming out of the wall. Maybe what we'll do is actually release all of our constraints a little bit early. Let's just, I'm gonna copy this value here, just so I have it stored on my clipboard, and set that value to release on frame 2. And maybe I'll set, yeah, I'm not going to mess with that one. Let's do, actually, you know what? I'm going to paste this in here. I want to actually release this one. I think this will have a more dramatic result if I release these. So I'm going to copy this one to my clipboard. $F is greater than 123. I'm just going to, I'll paste that back later I'll have it release at frame 2. And let's go back in and go to our camera and click play. Everything should fly apart pretty quickly, but you can see all these points are, you know, they're being released, but they're colliding. They're colliding with our wall. So they get released, but they hit the wall and bounce off of it a little bit. I don't see anything coming out of the wall. That's good. And, you know, if there is any thing we can, at this point, you know, we could cheat it in the end by maybe increasing the size of our room if we needed to, if we were noticing any weird intersections. It kind of looked like something was happening over here, but that looks like it's just a Z fighting issue with the viewport. So I'm not going to worry about that. And I'm going to say we're good. And we're going to go back to our Vellum solver, crank our collision passes up to 100. Go back to frame 0 and go over to our Vellum export, section. Go to our Vellum cache and click Save to Disk to write over our old cache with a new cache. So I ran my sim and I forgot to set my value back to. I forgot to set the Vellum constraint property value to. Back to release at frame whatever. So I'm going to click Control V in there to get that back. Thankfully, it's only about a 3-minute sim. So I'm going to go back to frame 0 and cache it again. Hit Save to Disk and I'll catch you on the flip side. All right, so now that cache is done, let's take a look at what we got. Click play. We've got our nice webs attached to the body. They're starting to break apart and then they release, and they all release when the spheres hit the ground. We've got no weird things going on underneath the character. It's all looking like it's working just the way we want it to, which is great. So now what we got to do is just export this stuff. And exporting splines to Cinema 4D is a little bit tricky, but the rest of it's pretty straightforward. So we're going to just take all this stuff out and import it into another network where we'll combine everything into an Alembic file. First thing I want to do is just see if there's anything we can do to post-process some of these wires. Right here, I just want to stop at a frame that's like pretty complicated, where you can see a little bit of jaggies. Like if I go right here and just kind of zoom in over here, you can see all these wires sort of have a little bit of kind of jaggedness to them. So I'm going to let's just get into our Vellum cache node over here. So you can see we've got some sort of jaggedness to these wires. So we can just do a little bit of post work on these before we export them, I think. And that'll make things look a little bit nicer. To visualize, I'm going to throw down a polywire, just to help me see, just to give these wires some thickness, just for preview purposes. I'm not actually going to export these because they're pretty heavy. You could if you wanted to, probably. But I think that it works better for me in general. It's much more a higher performance for me to actually mesh these wires at render time using Redshift. So I'm going to just bring the wire radius down a bit, like so, and just kind of look at what's going on over here. So we've got these intersections and tangles going on. That's all looking really good. Now what we could do at this point is maybe look at the Vellum post processor and see if that can do anything for us here. We could try to do a spatial blur, but if you notice, that actually starts to pull apart these points that we want to remain connected. So that's not going to work. But what I might do here is actually just throw down another resample. If I look at our points here, we can actually increase the resolution of these wires a bit, and it'll help make things look a little bit nicer in the end. So let's throw down a resample. And I'm going to set the resample to, I'm going to wire that in here. And instead of making it more coarse like this, I'm going to take the length down to something like 0.02. So before we had this many points, and now we have even more. We could even bring this down, maybe to even 0.01. So now we get many more points, but we've got these straight angles still where these lines were straight. It's still doing kind of this straighten thing, just adding more points along a straightened line. But if we go down to the straighten edges section here, or treat polygon as, it's treating it as straight edges, but we can turn it into subdivision curves, and that makes things even smoother. So that now when we polywire everything, turn these points off, everything's looking pretty natural and noodly, which is great. Yeah, we get some like really great wrapping around going on here. So this will be really fun to render. Hopefully, once we get it out of Cinema, or out of Houdini and into Cinema. So I think right now what I'll do is I'll just throw it on a null. And we're going to just, we don't want to take our polywire. This is just for visualization, but we want to take this, the output of this resample, and we're going to call this out strands, like that. And then we're going to want to create a new export node. So this is going to be, let's do, I'll create a geo, and I'll call this Alembic export. And in here, I'm just going to start gathering all the different pieces of our simulation that we're going to want to bring over. So things we're going to want to grab, we're going to grab these strands. So I'll just throw down an object merge in here, and we'll put our strands in to the object one. So we've got our strands in here. I'll just name these strands. And then we're going to want another object merge to bring in our rigid body sim. So let's go over here and select the animation, and I'll grab this RBD simmed character, bring that in. And then we're going to just, we're going to grab our room. And so I'm going to throw down another object merge, and we'll get this, call it the room. This one's going to be the animation, or I'll call this the character actually. And the room is going to be the, I'll just grab the original room right here. Cool. So now, if I merge these three together using a merge node, select all of them, drag them in, we have all the elements of our scene set up here. But a couple things I want to handle. First off, this room, I'm going to, noticing how it's blue on the inside here. We really don't need it to be, we actually want to reverse these normals. So I think actually what I might do is just delete this face. So I'm going to just select, well, let's go into our camera. So this is the angle that we want. I was selecting the wrong face, it looks like. I'm going to just zoom out. So I'm going to select the wall behind our camera and just delete it so that we can see into our object. Into our room, and then I want to click reverse, or I'm going to throw down a reverse node so that I actually am reversing the face direction of that room, so that when we're inside, everything's facing towards us, not away from us. So when I merge that together, you can see that's all looking good, but our normals are messed up on the room. So I'll just throw down a normal like this and wire that in. Now we get these nice hard edges like that. So that's looking good. The next thing is, it looks like we actually are going to need normals on our character as well. Oops, something got mixed up there. Our character will actually need normals. So I'm going to throw down a normal, another normal here, and that brings back our character geo looking great. And the strands don't have normals, and that's why it was creating an issue with this object merge. When you merge things together that don't have normals with things that do have normals, it can mess up normals, or it just, things get weird. So I just tend to when in doubt, throw down a normal node to get all that cusping to look right again. The next thing I want to manage is getting rid of some of the attributes we don't need. If we middle mouse click on this out strands, we've got all these attributes that we're not interested in. In fact, the only attribute we really want is the position, because it's actually, I have not really had too much success as of this version of Houdini and Redshift and Cinema 4D to get anything more than really the shapes of these wires in as an Alembic file. So we're going to throw down an attribute delete. And this is just sort of normal procedure when exporting geometry as an Alembic from Houdini, is you want to clean up all these attributes because it'll actually make your Alembic file huge if you don't. So we're going to delete all the point attributes by throwing in a star, all the vertex attributes throwing in a star, primitive attributes, and detail attributes. So stars all across the board. And in addition, we're going to get rid of all of these groups. We don't need any of these groups. So I'm going to throw down a group delete as well. And that's I'm going to set this to delete all the groups by throwing a star in there as well. So anything is going to be deleted. So we just have our position left, which is good. And then for our character, we're actually going to want to keep some of these attributes. We're going to want to keep our we're going to want to keep the color because we're going to use that in our shader. And I guess we could keep the normal, but I feel like if I get rid of it, if I get rid of it, it's going to cause an issue. So yeah, we're going to keep the normal for right now too. Actually, yeah, I don't know if I need the normal. Let's see. We'll see what happens. I'm going to grab these two attributes and just alt drag them over here. These two nodes. So yeah, you can see that it deletes our normals and our normals kind of go away. I think, I think what I'll do is I'll just leave these normals on. Instead of in our attribute delete here, I'm going to, I don't want to delete color. So I want to leave color on there by putting in a caret key and then saying CD, capital CD. And then in vertex attributes, I'll throw in another one and say capital caret N, capital N. So that keeps our normals in our scene. And then I want, for the wall, I want to do something similar. So I've got, I don't really have any attributes I want to delete, and I don't have any groups I want to delete. So I'll just leave that one the way it is. The other thing I want to do is at the end, we're going to want to create a, let's create a ROP Alembic output. This is what we're going to use to export all of this geo all in one Alembic file. But we want to be able to easily select different parts of our geometry. And we've got three major things that we're exporting, and we might want to shade them all differently. And certainly these strands are going to behave differently and have different properties because they're going to be rendered as Redshift splines. So we need to split this information up going into the ROP Alembic output. And the way I like to do that is to build hierarchy from attribute. That's this little thing right here. So I'm just going to tick this on. You can see that the path attribute is its default attribute that it creates. So if I go over here and from I like to use actually not the path attribute, but I create a new name attribute and I just do it by hand. So if I go over here to just further up in our network, and I throw it on a name node and wire this in here, I can create my little path. So I'm going to call this dancer is the name of our path, and these are the strands. So I'm going to call this dancer, and then I'm going to put in a slash and then call it strands. And this is building a directory inside of our Alembic file. So I'm just going to option drag this over here and over here. So here we've got our character. So I'm going to call this, I'm going to call this dancer character. And this one is going to be dancer slash room. And you can see up here the attribute is creating his name. So that's consistent across all of them. It's all a primitive class. Good to go. So down here, now in our Alembic output, we can choose our path attribute to be the name attribute that was created. So that's good. And the next thing we got to do is just go up here and select our output range. I'm going to render the frame range from 1 to 160 because that's where our bounds are set. But if your animation is different, you can change the length of that if you need to. And then I just want to put it out to a file. So I like to export everything to a file that is in the ABC export. So I'm going to make a new folder called ABC export, and then I want to put it into I just want to I just want to name my file based off of the naming convention I like to normally do, which is based off of the $OS, the operator, and or actually maybe I'm going to put backticks around the $OS and then underscore and then put more backticks around the $hip name. In fact, since I'm not exporting more than one object from here, I'm not going to name this after the operator. I'm just going to name it after the hip name. So if I ever version up my file name, it's just going to version this up, and then that's going to be the name of the Alembic file that we output. So here I'll still name this something reasonable like Alembic out. And here I like to put down a null, even though it's not 100% necessary. I like to put down a null here that is called the same thing. Alembic output or something like that. Cool. And so now, if we go back here, just gonna click on the Alembic output, or click on the merge. Yeah, the Alembic output actually isn't even wired there, so I'm gonna drag that back over here. And let's just go to our camera view and just click play and make sure everything's all in there. And everything's looking good there. So I think it is time to export our Alembic. So I'm going to hit save to disk. Should go pretty fast. Not even going to pause the video. Cool. So that has been exported. Let's see what we get on the cinema side. So I got my project file here in my ABC export, and I'm just going to drag this in here. You can see that what it likes to do is give you some options to import your file. I guess I'll by default scale everything up by 100 because we didn't do any scaling on the other side. So scaling everything up by 100 centimeters or up to 100 is going to be good. And over here under curves, it gives you this option to do hair if possible or splines only. I'll check hair if possible just to see if it does anything, but it doesn't always work this way. And in general, I tend to use as splines only. So we'll see if it gives us hair. And if so, we can explore those options. So yeah, it didn't. Not for this example, and that's probably because there's things like breaking happening, etc. But if I go in here and I can, now start to compose this scene, I could, I suppose, export the camera from my other scene if I wanted to, but we've got now our splines and our geo all in here, and you can see that actually on our character, we've got the color information here in this color tag right here, vertex color tag, which is good. And we've got our splines. So let's just focus on these strands for a second. How can we get these to render? Let's first off I'm going to throw down maybe, I'm going to just throw down a like a dome light. So let's go redshift lights, dome light, and just bring in the whatever default light is that comes in with redshift. It's just a blank white light, I believe. And I'm going to open up my redshift render view like this. And now we need to get these strands to show up. If I click render right now, nothing's going to happen. So I'm going to go to these strands, and you can see here, we'll just go under tags, redshift tags, and set a redshift object tag here. And you can see that it gives us the option to do curves. And we can change the curve mode to hair strands, boxes, cylinders, capsules, cones, strips. These are all different types of sweep geometry. So a box will make sort of a square that runs along these. It'll sweep a square shape along this. So you have sort of a four-sided tube. Cones will be sort of tapered. Capsules will actually put a rounded end at the end of each strings, and cylinders will just be sort of round without a rounded edge or rounded point at the end. So what I'm going to do is I'm going to use cylinders because I think that should probably be fine. And we'll leave all the rest of this, all the rest of these settings at default. And I'm just going to fire off a render to see how it looks with these default settings. So I'm going to hit the IPR play button here. And you can see that it is rendering our strand geo. So if I zoom in, you can see that it is circular or cylindrical geometry. And now it's just sort of a matter of setting your thickness to something that you like. Sometimes these strands, when you get to a really high number of strands, it can take a while for it to build the geometry to start rendering. But if you hang in there, it can actually handle quite a bit. Not to say that it would render it necessarily fast, but it can do quite a bit for sure. So now I'm going to just see what happens. I'm just going to turn the room back on. And it's kind of hard to see in here, but some of the light is coming in from the environment that we have. I'm just going to go and select my render options and go to Redshift. And under Redshift menu, under GI, I'm going to set this to brute force and brute force. And that isn't really doing much to get any light in here. I'll add another light. So let's throw down a Redshift area light. And that's sort of right in the middle of everything. We'll just drag this back so we can kind of see what's going on. In our room, you can see that these points are attached to the walls. These wires that have already snapped off are kind of colliding with the walls and the floor. So that's looking good. And the next thing that we can do is let's just look at the shading on our character. So I'm going to stop this render. And let's just turn off the strands and the room, and I'm going to turn on the character. And what I'm going to do here is just create a new Redshift material. And I'm going to put that on our character. And now what we can do is let's just fire off another render. And I'm just going to turn off this area, or turn off the dome light. You can see we just get this illuminated, these illuminated white spheres. Maybe bring the area light intensity down to like 50. So we get just these white spheres, but we want to actually color these random colors or something based off of the color information that we have on our vertex tag here. So I'm just going to stop that render for a second, and we're going to just quickly dive into our Redshift shader graph. So let's go into the Redshift material. I'm just double click on this tag right here and edit the shader graph. And that opens up this window right here, and I can look up a point attribute. So we've got this point attribute here. And I can wire this. I'm just going to wire this directly into the surface for a second, just to make it easier to understand. Now, this is actually a vertex color tag, so we might actually need to. I'm just going to drag this vertex color tag into the attribute name, and then I'm going to fire off another render to see if it's picking anything up. And it looks like it isn't. Because this is a vertex tag, it has converted this to a vertex tag. We need to actually use a vertex attribute. I always get these mixed up. It's all right. Just kind of got to try one, and if that doesn't work, we just do the other one. So wire this guy into the surface and go to the vertex attribute tag, and I'm just going to drag the vertex tag in here, and I'm going to fire off yet another render. And now you can see our colors are showing up on our output, and that's good. Just to troubleshoot, I like to wire these things straight in so I can see a constant color and not have to worry about what the shading is doing in the scene. But at this point, you could actually remap this color to whatever you want. You could throw it on a ramp, and say we have a color scheme we want to do. Let's wire this in here to the input. Wire the output of this into, let's just do the diffuse channel. So diffuse color. And then wire this into the output. And we don't need this point attribute. We needed the vertex attribute, so that's good. Now we can just sort of mess around with this ramp and get new values for our color scheme that we want to do. So let's say we want to do, let's do I don't know. Let's start with a color. Oops. Let's start with a color that's like something like this teal greenish color like that. And then we could do another one that is maybe a good purple like that. And then we'll do a white color that looks good. I'll actually maybe Maybe control drag this one out and control drag this one out. So we do get a little bit of gradation, but not too much. And we'll just go with something like that in our scene. And so that's cool. Then we maybe could add something to our room. Let's just create another redshift material. And I'm going to call this first one, this is the, this is going to be the spheres. And this one is going to be, whoops, this one is going to be the room. And I'll put the room on the room, and we'll just maybe make it a nice, let's say, I'm going to turn the reflectivity down and make it a nice kind of a matte light white color for right now. Always change it later. And we'll create another shader for the strands. I'll call this strands. Don't need that. And I'll put the strands shader on the strands. And maybe we'll set these strands to be, let's set these strands to be something like, oops, not that. In the color, we'll set it to them to be maybe we'll do a nice yellow color. Something a little bit on the warmer side like that. Cool. All right, so now let's turn all those on, and let's turn on our dome light. I don't know if it's really going to change anything in here, and let's do one more render. All right, and it looks like we're off to the races with the old dancing mocap person. So now you should be ready to go and light and shade and tweak and get this thing all looking nice, because after all, what would a good old Houdini for Motion Designers course be without a nice mocap dancer that was attached to some vellum strings and rigid bodies and doing all sorts of fun physics stuff, like the old Method Studios AICP reel style, you know, that was super inspiring from a couple years ago. I hope that you found that this was fun. This wraps up the vellum chapter. I think that I think that this vellum stuff is all very new. It's all constantly being improved upon, and it's super useful, and to the point where I don't even know what I would have done prior to this. There are other solvers in Houdini that would have accomplished things like this, but vellum has made it way faster to get these kinds of effects, and super fun to work with because of that quick visual feedback that we're getting ever more accustomed to with the increasing speeds of render engines and everything like that. All right, so that wraps us up for the vellum chapter. And in the next chapter, we're going to be looking at how we can create our own smoke simulations and fire simulations, and how we can use that volumetric simulation to advect particles to make even more interesting layered simulations. So stay tuned for that, and I'll catch you in the next chapter.